How would I know?
Yes, it's up.
All right. Okay, so let me first ask you guys a question. Shall I redo the Laurent series derivation, which we started at the end of class last time? Would you like to see the construction again?
Yes.
Is that a yes? Okay. I suppose that. All right, so, so the deal is the present homework is due when?
Today.
There's one homework due today, and then the next one is next Tuesday. Is that right?
Next Friday.
Next Tuesday is what you said, so we're doing every Tuesday.
Every okay.
So we're just going to stay with Tuesday.
All right, I will try to. All right.
I have a question real quick about
Yes.
the homework.
Sorry.
I couldn't get that. Usually for homework we have said that we've been doing 14 problems, and this other homework is like 17 problems. Do you want us to just do 14 or do them all? Because I did them all just in case, but
What
like
do they do?
today.
Yeah, on the website.
Yeah, it was on the website.
Well, I mean, in as much as it's already today, why don't we just say do them all? But the fact is that you know, the grader can't grade them all. So
Yeah.
if you missed one or two.
Hopefully it's not the ones he grades.
Why don't you send the grader an email saying, please don't grade the last 2 or 3 problems.
Sounds good.
All right, so I'm going to redo the Laurent series. And the basic thing here is that what we've got is, let's see, I feel like using colored chalk occasionally. We've got some singularities. And we want to evaluate a function at some point z here. And then we've got some other singularities that are outside, maybe there and there, and over here on the lousy blackboard. Okay? So, what are we going to do? What we do is we integrate this way. Okay, and we're going. Okay, so that's our contour. And you see the contour encloses the point Z. And it's such that the contour lies within a simply connected region. The simply connected region is the region, you see, you can't connect these two and say it's simply connected, but it's rather that the region from here around and from here around, that's simply connected, and that's a region of analyticity. So we can say, and let me just label these, this is contour C1, this is contour C2. I should have called them C outside and C inside, but okay. And the combined contour is C12. So we have that S of Z, F of Z is 1 over 2 pi I, the integral of F of Z prime dZ prime over Z prime minus Z, where this is on the counter C12, and C12 is basically C1 plus C2. And how you divide this up is, well, all right, let me say the C12 contour is the contour that I drew on the board. Now we make some changes. what we do is we say, well, if we run these two contours together, we shrink the difference between them, they'll just cancel. And once they've canceled, we have two separate contours. That's what this means. And moreover, this contour is counterclockwise, which is the convention. This one's clockwise, but a clockwise contour is minus the counterclockwise contour. So now what we do is we say f of z is 1 over 2 pi I, the C1 contour, f of z prime dz prime over z prime minus z, minus 1 over 2 pi I, the C2 contour, and okay, now both contours are clockwise, counterclockwise contours at this point. The next thing we do, though, is we recognize that Z0 is the center of both circles. These are circles. I didn't draw them as perfect circles, but I meant to. Okay. And so C1 and C2 are perfect circles. Z0 is their common center. And so what we can say is that Z double prime minus Z0 over Z minus Z0, and let me now say which is Z double prime. This one is Z double prime. So Z double prime is C2. On the C2 contour, Z double prime, so this one is Z double prime. And this one is Z prime. So Z double prime is closer to Z0 than Z is. And so we've got that this is less than 1 on C2. On the other hand, on C1, we have Z minus Z0 is less than Z prime minus Z0. So on C1, the points Z prime are farther from the common center than Z is. Okay, so we clear on that, just the geometry of circles. And now the next thing we do is we add and subtract Z0 from these two denominators. And on this bottom denominator, because we've got a minus sign here and we don't like minus signs, we absorb the minus sign into the denominator and make it Z minus Z double prime. So then what we have is f of z equals 1 over 2 pi I integral C1 f of z prime dz prime over z prime minus z0 minus z minus z0. So there I've just done nothing here. We've just added and subtracted z0. Now, because we've absorbed this unwanted minus sign into the denominator, what we have in the denominator for the second one is 1 over 2 pi I integral C2 z double prime dz double prime over, and now it's z minus z0 minus z double prime minus z0. So the z0's cancel in both cases. But now we factor the denominators, and I think I'll take advantage of the blackboard here and write them this way. And what we'll do is we'll pull out z prime minus z0 and what's left is 1 minus z minus z0 over z prime minus z0. That one. And then this one is 1 over 2 pi I integral c2 fz double prime dz double prime. And now we factor out z minus z0, this term. 1, and then it's minus z double prime minus z0 over z minus z0. Okay, so that's our expression. F of z is the sum of these two integrals. Now we realize that this is our favorite expression. 1 over 1 minus epsilon is the sum epsilon to the n equals 0 to infinity. This is the physics graduate student's friend, because you can use it in many, many cases. It's probably the most useful formula in this, of course, is for epsilon less than 1. And so now, and this thing for epsilon less than 1, this is converges absolutely uniformly and so forth inside that disk. And or if it's uniformly, I should say, if you take any circle, if you take any disk of radius less than 1 and include the perimeter, that's a closed set. It converges uniformly and absolutely on that closed set. Okay, so we can expand these integrals as we interchange summation and integration, and what we have then is sum n equals 0 to infinity, z minus z0 to the n, 1 over 2 pi I, integral c1, f of z prime, dz prime over z prime minus z0, and now it's the power n plus 1. So it's the power n from the expansion here, and then plus 1 from this guy. And this second sum, I'm going to change the variable to m. m goes from 0 to infinity. And what we are pulling out now is we have this thing raised to the power m, and so we have z minus z0 to the power m plus 1, but in the denominator. So we have 1 over z minus z0 to the m plus 1, 1 over 2 pi I, integral c2, and what's left here is z double prime minus z0 to the m. Okay, so that's the Laurent series, and what's traditional is to rewrite this in a more compact way. And the way we write it in a more compact way is we say, well, let's let m be minus n minus 1. Or equivalently, let n equal to m plus 1. No, I've got that wrong. N is equal to minus m minus 1. And so then we can combine these two terms. In other words, we can say m plus 1 is minus n. That's the third way of writing it. And so we'll call this minus n. And when we do that, in fact, what's bothering me just, all right, well, we're going m equals 0 to infinity, but notice that the case in which this thing is equal to 0 doesn't occur. Because the, when m is 0, we still have the first power here. So it's 1, 2, 3, and so forth. And so the total thing then is sum n equals minus infinity plus infinity. Z minus z0 to the n, 1 over 2 pi I, integral f of z prime dz prime over z prime minus z0 to the n plus 1. And now I'm going to call a contour C, and this contour C can be any contour between contour C1 and contour C2. So it could be C could be this thing. And of course, counterclockwise. Did you swing this around? So in other words, C can be this contour here, any contour between the outer contour and the inner contour. All right. So this is called the Laurent series, or that Pierre didn't live very long, died at the age of 41. All right, this series is often written as f of z is the sum an of z0, z minus z0 to the n going from minus infinity to plus infinity, where an of z0 is 1 over 2 pi I integral f of z over z minus z0 to the n plus 1 dz. And see, we don't immediately translate that into a derivative because these n's can be negative. There's a special case, a minus 1, which is 1 over 2 pi I integral. When n is minus 1, this goes away, and it's just f of z dz around this contour C. This is called the residue. Not quite sure why, but anyway, it's called the residue. And we'll see that we can say a little bit more about that later. Now, so this is a general Laurent series. Now, let's go back to, as we turn the camera around, let's go back to this original picture. So suppose we had some singularities in here that were isolated, single poles, double poles, so forth. Well, of course, I haven't talked that much about singularities, and so maybe I should right now. So if you have a function that is analytic everywhere, that's called entire or holomorphic. It has no singularities anywhere, although people sometimes like to think of, well, clearly, remember those inequalities we were talking about last week. Namely, that if a function's entire and bounded, if it doesn't increase without limit as you go out into the complex plane, then it would have to be a constant. So all these entire functions get big if you take z out in some direction far enough. And people like to call that the point at infinity. Why they think of, almost the entire complex plane as a single point is a little weird, frankly, or it's puzzling, let us say. Why is puzzling, and to do it is a little weird. But it's something that people do, and they call it the point at infinity. Anyway, a function that has has a singularity at some point, but is analytic in some disk around it, that's said to have an isolated singularity. So an isolated singularity is what you think. Namely, you have analyticity around the singularity, but something goes wrong at one point. If you have f of z looks something like this, 1 over z, this is said to be a pole of order 1. If it's f of z equals, say, 1 over z squared, it's a pole of order 2. Or in general, if you can say that, say, z minus z0 to the n, f of z is analytic at z0, but z minus z0 to the n minus 1, f of z isn't analytic at z0, but rather has an isolated singularity at z0, then this is called a pole of order n. And as you can see, this is pole of order 1, pole of order 2. Pole of order 1 is also called a simple pole.
Does this logic work when you have a whole neighborhood of singularity? Because if I want to say something is continuous at z0, I have to approach it from somewhere. And so that I see how this works if you have a pole that is just sitting isolated. But would it work if you had a neighborhood of things?
Yeah. Well, the idea is we're talking here about isolated singularities.
Okay. This is for isolated. Okay.
Right. And a function that only has poles being these things like 1 over z minus z0 to some power. Function that is otherwise analytic, that's called a meromorphic function. Meros is a Greek word for part, holo or holos is whole or entire. Anyway, again, in Greek. So let's see, what was I going to say here? Yeah, in general, this function f of z that we're talking about here, the way I drew it, it had isolated singularities. So it's presumably some meromorphic function. Well, if these things are poles of some order, then the corresponding, here, let's rotate the camera around again. The corresponding sum isn't going to go from minus infinity. It instead will go from some value L. So typically, if you have if f of z is meromorphic, that is just has some poles, then typically the expansion is f of z is some sum from n equals L to infinity, an of z0, z minus z0 to the n, where L, it might be minus 13, or if the thing is entire, it might be 5. And so that's basically a more common case is where L has it's just some finite integer rather than minus infinity. For these functions, you can pick off these singularities. You can say, or these coefficients. You can say a sub L, well, it's the limit of z minus z0 to the minus L times f of z. Z going to z0. So suppose L is minus 2. Then the leading term here is 1 over z minus z0 to the minus 2. L is minus 2. And so you multiply by z minus z0 squared and take the limit, and that gives you the first coefficient. And then you can subtract it off and get the second coefficient. You can say a sub L plus 1 of Z0 is limit now Z minus Z0 to the minus L minus 1. I'm wondering if I'm right with minus 1. That maybe should be a plus 1. F of Z minus Z minus Z0 to the L, a sub L of Z0. So let's see, suppose that a second order pole, we pull that out, and this one then was, yeah, no, this is correct. So this would be, if L was minus 2, this would be 2 minus 1, and so we're only using 1 power of Z minus Z0 to solve the singularity. We've already pulled out the minus 2 singularity. So this is one way of constructing the Laurent series. The more general way, of course, is to say that an of Z0 is just this integral, and you just do the integral. An example of a function with poles is, for instance, f of z is an infinite product here, j equals 1 to infinity, 1 over z minus j to the j. All right, so this has a pole at every positive integer. The first pole is a simple pole, the second one is a pole of order 2, and at j it has a pole of order j. It is meromorphic because it's analytic except for poles. In fact, another example is the gamma function, which we'll come to in a moment, but before we get to the gamma function, let me say something about what's called an essential singularity. So an essential singularity is a pole of infinite order. Okay, as an example, suppose f of z is e to the 1 over z. Okay, so now as z approaches 0, you can see that f of z goes nuts as z approaches 0, right? Because first of all, z can approach 0 in many different ways, and it can be either extremely big or extremely small, all kinds of complex values. In fact, there's a theorem due to Picard, which is that if f of z has an essential singularity at w, then inside every disk around w, f of z takes on every complex number, with at most one exception, an infinite number of times. Okay, so let's illustrate that for this function. The exception it doesn't take the value 0, but basically every other, it assumes every other value an infinite number of times. And let's see how we could do that. We could say that this could be e to the log r, where r is some positive number, plus I theta plus 2 pi I n. So now, as you spiral in, 1 over z can be arbitrarily big. So you get all values of positive log r. Moreover, the argument of 1 over z, the imaginary part, it's 1 over z is equal to absolute value of z squared x minus iy. So as you spiral in there, the imaginary part is y over z squared. And if we let x equal 0, then so in other words, if you come in on the real axis, close to the real axis, no, on the real axis, this goes to minus iy over y squared, which is minus I over y. So now, now I've said x equals, I'm actually coming in on the imaginary axis, I misspoke. Now, as we go very close to 0 on the imaginary axis, this assumes all possible imaginary values, and that means you get all phases, and you've hit them an infinite number of times because this n, every time this n increases by 2 pi, or n increases by 1, 2 pi I increases by 2 pi I, and that makes no difference to f of z. So you hit the same number an infinite number of times, every complex number except 0 in this case, because there's no way, although you can make this arbitrarily small, you can't really make it to be 0. So that's, I don't know why I went on so long with that example, but maybe just to show you how spooky infinite, how spooky these singularities are. And in fact, the Laurent series for this e to the 1 over z is just a sum n equals 0 to infinity 1 over m factorial 1 over z to the m. And so this is the sum n equals minus infinity to 0 1 over absolute value of n factorial z to the n. So you see the Laurent series goes to minus and it goes from minus infinity and then it just poops out at 0. All right, so let's look at a simpler case, a meromorphic function with 2 poles. So here f of z is 1 over z, z plus 1. And we'll write it down as a Laurent series, so it's minus infinity plus infinity an z to the n. And because literally a sub n is, well, all right, let us see. A sub n is 1 over 2 pi I, an integral on some contour, dz over z to the n plus 2, z plus 1. So in other words, that's f of z stuck in there, and this is z n plus 1. So that's this, so I guess we have to go all the way back to these two formulas. So the camera. So in other words, these two formulas. So a sub n is this integral here. And there, I'm doing this Laurent series about z0 equal to 0. That's why there isn't any z0 in this. And in particular, the contour C is this contour Z will be some r e to the I theta, where r is strictly less than 1, and theta goes from 0 to 2 pi. And so, one way to do this integral is to say, well, once again, to use the graduate student's friend, 1 over 1 plus z, in as much as I'm doing this about z equals 0 and z is going to be r e to the I theta, and r is less than 1, then this is the sum minus z to the m equals 0 to infinity. And so when we stick that in here, we get 1 over 2 pi I sum m equals 0 to infinity, integral on this contour radius r, so c sub r, minus z to the m from this z plus 1 expansion, and then z to the n plus 2, and then, of course, dz. And now if we let z equal r e to the I theta, you see that this is a sum 1 over 2 pi I, integral is minus 1 to the m. This is e to the I m theta, r to the m. dz is I r e to the I theta. d theta, we're going now from 0 to 2 pi. And down here we've got r to the n plus 2, e to the I n plus 2 theta. And so what do we have in these theta integrals? We have n plus 1 upstairs, n plus 2 downstairs. So basically this is going to be 0 unless n plus 1 is equal to n plus 2, or m is equal to n plus 1. And in that case, the integral is basically 2 pi, and then there's an I, so that cancels. So we have a sum m equals 0 to infinity. This minus 1 to the m, then it's r to the m minus n minus 1, but then it's delta m n plus 1. That's this condition here. And now that just means that there's basically as we do the sum on m, what we get is minus 1 to the n plus 1 period. So that's what it is. A sub n is minus 1 to the n plus 1. And consequently, we get f of z, which of course is the series from z plus 1, equal to a sum n equals. And what about m? Well, m was non-negative. And so m can be 0 or higher, so n can be minus 1 or higher. And the value is minus 1 to the n plus 1, and then z to the n. So that's the, so let's swing the thing around. In other words, it's an of 0, because we're expanding around 0, z to the n, and a sub n of 0 is this integral which we just computed. Okay, so maybe swing it back around. There's another way of doing this, of course, that's much, much simpler. Namely, we just say f of z is equal to 1 over z, and now we use the graduate student's friend formula, and write this as sum n equals 0 to infinity, minus 1 to the n, z to the n. And so, once again, we get a sum n equals now minus 1 to infinity, minus 1 to the n plus 1 z to the n, which is the same thing. So those are two different ways of getting to the same result. All right, so are there any questions while I grab a shot of coffee? All right, the next topic is, you might think of it, it may be, some people might call it a curiosity. It's not the most essential part of complex variable theory, but the thing about complex variable theory is that it's just amazing at how many results that one can get, and one of them is the argument principle. And the idea is to consider an integral like this, an integral over a contour, f of z, and now g prime of z over g of z. So this is like the derivative of the logarithm of z. And as usual, we'll put this 1 over 2 pi I. And the idea is that f of z is analytic in some region that's simply connected, and g, on the other hand, has simple pole, has some isolated poles. So g is meromorphic, so I think it's better to just say what that means. Isolated poles. Yeah. So G has isolated poles, F is analytic, we've got some simply connected region. And now, the key point is to look at what this looks like near one of the poles. Because clearly, apart from a pole, unless this thing is singular, this integral is going to be 0, because the integral of an analytic function on a closed contour. So let's see how it behaves for a simple G that has a pole of order, well, minus n is the way I've written it. But anyway, let's just say G of z is a sub n of w z minus w to the n. So there I'm imagining that G has a Laurent series, and I've just pulled out one term. So all right, let's swing the camera around again. So imagine that G has this series, and we just look at one power, n equal to m, where a sub m would be given by this expression with f replaced by g. Okay, so now if G looks like that near W, what is G prime of Z over G of Z? Well, you know, you learned in college how to do that, and it's just the derivative is n of W z minus w to the n minus 1, and then we divide by an of w z minus w to the n, and altogether it's n over z minus w. So in other words, you pick any term in the Laurent series for the meromorphic function g, and you go to this point w that's some sort of a singularity, or it could be a 0 or a pole. No matter which it is, you always get 1 over z minus w, you always get a pole. In other words, this g prime over g always gives you a pole, even if g minus z were z minus w squared. And the reason is that there's a g there and a g prime there, so it generates a pole. A simple pole in every case. And if n is positive, then that means that G had a 0 of order n, but still G prime over G has a pole. And if G actually had a pole of order -2, say, this would be -2 over Z minus W, still a pole. So in other words, when we do this integral, that integral, what we're going to get is 1 over 2 pi I, and if we go around the point W, we're going to be getting f of z n over z minus w dz, and then by, well, dz. And then by Cauchy's integral formula, this is just n f of w. Okay. So this is a remarkably amusing formula. In other words, we've got some meromorphic function whose series is 8k w z minus w to the k, and we're imagining that there are no essential singularities, so we actually are going from some n to infinity. Then what we get is 1 over 2 pi I integral c f of z g prime z g of z dz. So we've got this thing here, and now we can imagine shrinking this contour, and we've got these various points in there. Let me get to this purple chalk that maybe you can illustrate this. We've got these various points that are either zeros of G or poles of G, but we shrink this down so that we just get these guys like this. In other words, we just have tiny integrals around all the singularities or zeros of G, but those singularities or those poles or zeros of G are poles of G prime over G. And so this is equal to a sum over all of these zeros and poles, n sub L f of w sub L, where the n is the n that came from this n. So a 0 gives you something positive. So the zeros, n sub L greater than 0 for zeros, n sub L less than 0 poles. All right, let's just check the sign of that. If this is a 0, so n is positive, positive for zeros. And just between you, me, and the internet, I think there are two ways of writing zeros. You can either have an E or not have an E. I suppose leaving the zero, the E out is probably simpler. Okay, so this is called the argument principle. And no idea why it's the argument principle, any more than I have any idea what that means. Let me erase that and go on. Okay. So the next topic is a topic that people always talk about with almost a religious reverence, and it's called analytic continuation. There are examples of it, but I really have not seen all that many examples of it. We don't. I suppose maybe it's just we do it implicitly and don't think about it. Anyway, let's just think about FFC for a moment as a suppose it's analytic within a circle of radius big R. And so we can write this as a sum 0 to infinity z minus z0 to the n factorial, the nth derivative at z0. So we've got analyticity inside a certain circle. And we imagine z0 is the point here at the center. And so this converges everywhere there. Okay, now, what we can do, you see, is we can, suppose here, let me get the purple chalk now for writing the nearest singularity to z0. Suppose it's over there. Okay. So what we can do, just as a guess, is we can try to do a power series around z1. So z1 is inside the region of analyticity that we're guaranteed. And so we start writing this as sum z minus z1 to the n over n factorial, and now fn of z1. What often happens, not always, but certainly sometimes, in some cases, frequently, anyway, sometimes it happens that this power series has a wider range of convergence. In other words, if this were the only singularity in the function, for example, then although z0 only has a radius of convergence out to r here, if you do it about z1, well, your radius of convergence might be 1.5 or 1.8 times r. In other words, you might be able to have now a radius of convergence like that. And then once you do that, you can expand around z2. And well, that might have a radius of convergence like that. So this is called analytic continuation. You can often continue a function and find a wider range of analyticity. And one example is, once again, the graduate student's friend. If you have f of z, sum z to the n equals 0 to infinity, well, this has a power series that only works for r equal to 1. But if we use the friendly formula, we can sum it to 1 over 1 minus z. Now we've got a function that's meromorphic and just has a simple pole at z equal 1. It's analytic everywhere. So in a sense, we've analytically continued, by doing the sum, we've analytically continued from a circle or a disk of radius 1 about 0 to the whole complex plane except for the point 1, z to the 1. That's an example of analytic continuation. A more, how shall I say, a more profound example is the gamma function. So let's see. Somebody's asleep at this. I think I need a coffee addict to run the phone, the camera. Somebody who's like this all day long. Not people who fall asleep, and possibly not people who pay attention, because if you paying too much attention to mathematics, you don't realize that you need to turn on the phone. All right, let's go to the gamma function, and this is a very important function in mathematics. In fact, it's even in C and Fortran libraries, there are, you just need to say gamma of z, I think, and it'll compute it for you. Okay, 0 to infinity. We've seen this before in chapter 4. E to the minus t, t to the z minus 1, dt, and we can think of it as z minus 1 factorial. So this, of course, extends factorials from integers to complex numbers. Now, if we look at this integral, well, the integral converges only for real z greater than 0, because what we've got here, when the real part of z is greater than 0, then what we've got here is we might have 1 over z. We don't have 1 over t. We have 1 over t to the maybe 0.9. And 1 over t to the 0.9 dt, that's an integral you can do, it's finite. But but dt over t is log, integrates to the log, and log of 0 is minus infinity. So that's why real z equals 0 is a problem. But remember, there's an identity, and the identity is gamma of z plus 1 is equal to z gamma of z. We proved this last time. And so this says that gamma of z is equal to gamma of z plus 1 over z. Now, this thing obviously has a pole at z equals 0. But the numerator is well defined as long as the real part of z plus 1 is greater than 0, which means the real part of z is greater than minus 1. So all of a sudden we've extended this. Originally we had analyticity in the right half plane. Now, by writing it this way, we have analyticity up to minus 1, and we can close it all this area here. Again, apart from a singularity here, and now a singularity at minus 1. And now we repeat this and we say, well, 1 over z plus 1, gamma of z plus 2. Now we've got a pole at 0, a pole at minus 1, and now something going wrong at minus 2. Okay. And so we then write it as 1 over z plus 1, z plus 2, and then this is gamma of z plus 3, and so forth. And then what happens is you get the picture of gamma of z that you can find if you Google wiki gamma of z. You'll probably get a very nice three-dimensional picture in which for real z positive, everything is more or less okay. And then as you go to minus 1, minus 2, minus 3, minus 4, you get these crazy, you get these poles. They're just simple poles though, and so forth. So in this way, the function gamma of z that originally was defined by the integral on the right half plane, we've analytically continued it to the whole complex plane, except for an infinite set of poles at the negative integers and at 0. That's a really important example of analytic continuation. And then, if you want, you can look at equation 5.104, which is Weierstrass's formula. Yes?
Does this only work if each successive region completely encompasses the previous region? Or can you start working your way around by overlap?
I think you were right in the second time. In other words, you can start with the thing here, and then you might be able to extend it to here, and then there, and then there, and so forth. You know, who knows what the, you know, what I mean, for an arbitrary analytic function, you know, the region of analyticity could be, you know, anything, I suppose. When I say it could be anything, I don't know. There may be some theorem that I've never heard of or forgotten, which says that regions of analyticity always have certain shapes, I don't know. But we're talking about every analytic function, so the regions must be pretty much arbitrary. And, but I mean, clearly, if the function's meromorphic, then it just has some isolated singularity. So then, somebody, in fact, you could write down its, let's see. I mean, then it is defined as an analytic function everywhere except for these isolated singularities. Now, whether there's some easy way of analytically continuing, presumably you could just do it by the method, the crude method of do a Taylor series, do another one, and eventually you get the whole complex plane apart from the isolated singularities. All right. I think I'm going to skip the next example, but I must tell you that, well, for one thing, I have a mild cold, which I got from my wife who has a serious cold. And the TA, Keith Sanders, said he was feeling bad today, so he can't show up. What I can do is I can hang around and I guess do part of the problem session. But on the other hand, since I have a cold, which, yeah, it's, in my case, it's sort of mild. It's quite mild, but maybe it's not too smart for me to do the problem session because some of you may have no immunity to this particular virus, so maybe we'll just cancel the problem session. Okay, so there's this other thing called the calculus of residues. I don't know, it seems to me that's a very pretentious name. And I've never seen an example of it that was useful, but maybe I just have a funny background. I don't know. So let me go through the usual public service announcement for the calculus of residues. All right, so let me go back to the beginning. All right, well, it's certainly true that if you integrate f of z dz around a contour, this is a value. This gives you some integral, and the value is the same. IC is the same thing as IC prime, as long as C and C prime can be deformed into each other without crossing the singularity set. And so if we're considering an integral along some counterclockwise contour, then what we can do is we can always, suppose this is the contour, and where's that purple chalk that I was using for the singularity? Oh, here we go. So we've got some singularities here and there and there and there, say. Then what we can do, if this is our integral, then we can shrink it, and it's the same thing as that integral. And in fact, it's even the same thing as this integral plus this integral plus this integral. So in other words, as we shrink the contour, let me just draw the intermediate contour, the one that looks like, unfortunately, looks like a dead cow. But anyway, if I shrink this contour, what I'm talking about is going around this one, down, around that guy, back, over here, down here, around this way, up and back. So this was a contour. I've shrunk this whole contour. In other words, we've got these three singularities. We shrink this first from here, then to there, and then we really shrink it down so that these two guys cancel because they're going in opposite directions. And so eventually we just have those three, and then we can shrink them down to size epsilon or something. And what we get then is that this integral is just the sum, k equals 1 to n, in this case 3, of the integrals ck around each of those singularities. So fz dz around each of the poles, and these things are just 2 pi I, oops, no integral sign. They're just 2 pi I times the sum of this thing, in other words, is a minus 1 of the singular point, zk. K equals 1 to however many there are. And as I said, in this case, z1 would be here, z2, z3, so there would only be 3 of them. And so that's called the residue theorem. So the residue theorem is, you've got a function that's baromorphic, so it just has these isolated singularities. You can shrink the contour so it's sort of like it's the two-dimensional analog of, the shrink-wrapped packaging where you buy something in the store and it's covered with plastic or cellophane or some funny thing, I don't know what it is, some polymer. Whoops, I almost lost this on the floor, I'm sorry. Anyway, so you shrink wrap the thing, okay? And when you do that, you just get a sum of the residues. The residues just being the integrals around those little singularities. And so in general, you have to do each of them. If they're simple poles, then it's okay. So let's look at the case where it's a simple pole. Then what we've got is a minus 1 of w divided by z minus w plus the sum an of w, z minus w to the n. So this is the case where zf just has a single isolated pole, and so this is the case L equal to minus 1 for the Laurent series. And then a minus 1 of w, well, this is just the limit of z minus w f of z as z goes to w. So you can compute it this way, if you can evaluate f of z, or the same thing is just 1 over 2 pi I, integral around w of f of z dz. So those are two different ways of doing it. And then a third way of looking at these things is you take this integral of f of z over z minus w dz, and this is really 2 pi I a minus 1 of w. Now let me make sure that that's actually, this is 2 minus 1, this is the residue not of the function f of z, but of the function f of z over z minus w. So this is, maybe I should call it b minus 1, but it's the residue of this function. And this is then 2 pi I, the limit z minus w, f of z over z minus w. And that, of course, is just 2 pi I f of w. Of course, this is just a rewriting of Cauchy's integral form. So we have 1 minute left. Is there a question? Yes.
Does this get broken?
In fact, I didn't give you a handy of your previous question, so you get 2 now.
Okay. Does this break if you have a pole that is essential?
I'm sorry. Oh, if you have, you mean if you have an essential singularity?
Yeah.
And so suppose we have an essential singularity. What's the question now?
Well, so then when you're integrating right around your essential singularity, you're taking all the values, all the field values.
All right, okay. So let's think about this. All right. So let's suppose. So suppose f. So you're saying, what if f of z has an essential singularity at, say, w? And then suppose we're integrating this thing. And, that's, I think what happens is that when you try to integrate that around this contour around W, I think you have problems doing the integral. Let's see, you could always write it as an infinite Laurent series. And so what this would be, using that formula up there, is this would be a sum, minus infinity plus infinity, an of W, z minus W to the n. But you then have to imagine doing this an of W being that 1 over 2 pi I integral of f of z over z minus W, and the power is n plus 1 if I'm not mistaken. And well, so the question is, would these integrals converge or not? When f of z has an essential singularity at W, these integrals might not converge. We could look at the case. Well, we looked at the case e to the 1 over z, and we were able to write down the Laurent series with no trouble at all. So, so at least in that case, there was no problem. You could write down in other words, the analog of the residue theorem is that you need to, where is it? You need to include the residues, but, well, see, this is the case, well, let's put it this way. The function has I don't know whether the residue theorem in its simple form would work, but certainly the series, even though the function has an essential singularity, it may have a Laurent series, and in that case, the Laurent series may make perfect sense. So, I guess you have to look at each particular case. I don't know. I hadn't thought about that case. Anyway, I think we're way over time. Let's just quit.